All right, good afternoon, everyone. Welcome to today's seminar. It's my absolute pleasure to welcome back to our Dr. Taesang An. Received his PhD, master's and PhD in 2011 from Western University Civil Engineering. And Dr. Jack Wall received his master's and then PhD in 2017 from Western Civil Engineering. They both now work at APOM as geotechnical supervision. Dr. Taesang Ang is the geotechnical lead for Ontario. So a lot of interesting projects across both the coal and the mining sectors. And Dr. Jack Wall is a geotechnical engineer with APOM as well, based out of the Mississauga office. So it is an absolute pleasure to have you guys back, to have you guys on the other side of the seminar. So with that, please, the floor is yours.
Okay, thank you, Dr. Lee. So it's always a pleasure to be back to my school as alumni. And then, about 12 years ago, I was sitting on this same seat over there, right? And then, especially this seminar, I don't know who actually planned this schedule on the after the lunch, right? And especially as a warm weather, and then after lunch, and then most of the people just sleepy, right? And especially, the topic is more theoretical or lots of mathematics, and then it's quite boring, right? And then it's easy to sleep, right? But hopefully today's seminar, this topic may be attractive to you. Okay. All right, so today I'm gonna be introduce one of the AECOM's major project in Canada. So which is the Gordie Howe International Bridge. You know that where is the Windsor, and then we are building a new bridge between Windsor to Detroit, and then also including port of entry, both sides, and then main bridges, and also is connecting to Highway 401 in Canada side, and then I-75 to United States. Okay, so today's agenda. So I'm gonna be introducing the background about the project a little bit, and then as a geotechnical engineer, so we have to know that regional geologists and then local geologists how you can dealing with all those soils, and then principle of the surcharge and weak drain. So you already know that what is the consolidation of the clay, and then how you can accelerating those consolidation using surcharge and weak drain. And then we just a little, just quick touch about the design criteria, because of the all the project, public or private project, there is a project agreement, and then we have to follow the project agreement for our design. And then our design after design, and then one of the important thing is that as a P3 project, private partnership project, is that mostly design build, and then we have to verify our design, whether it's going to be actually a behavior of the soil, what we predicted during the design phases. So back analysis, and then we have to do some remediation work due to some different behavior. And then I'm going to be share some site photos, and then recent progress of the construction, and then conclude with the some conclusion on this project. Okay, so this is the project. So this is rendering. It's not actual. Looks like that because but almost like a maybe couple of deck is gonna be remaining for make these bridges at this moment. And then Gordie Howe International Bridge project is one of the largest public-private partnership infrastructure in North America. And then it's about the whole cost of the design and the construction. $6.4 billion. And then the length of the project construction is about 84 months. And the design life is 100 years of life. So this is the kind of will be a landmark in Canada and US in Windsor area in the future. So you can see that this way, right? So this is the length, about 2.5 kilometers. Of the cable stay bridges, and then we don't have any piers in water, so that's why this tower should be very, very high. So if you go up to the tower, and then you can see all around the place. and then you have to take the elevator and then go up to there. And then it's very, very scary too. Okay, so you know that everybody probably know that where is the Windsor. So we have Windsor here, almost like a west and then the south, maybe city in Ontario and or even Canada. And then Detroit is just over the Detroit River. And then there is a two existing route go to the United States. One is the Ambassador Bridges, and then which is about 100 years old bridges. And then another one is tunnel. So Detroit tunnel through the downtown to downtown. And then, but the government of Canada wish to have a connection with through the 401 directly to the another bridges, which is Goryeo bridges. So this one is the site of this project. And then today, so we're gonna be covered mostly Canadian POE entry. So about all the building design, but this project is including main bridges and the Canadian Port of Entry, US POE over here, and then Michigan interchanges, they're gonna be connecting with the I-75. And then Canadian Port of Entry, including 9 buildings. And then we have a return bridges to the Canada. So if there is something wrong on your way to United States, and then you have to go back, right? So then there is a return bridges. And then our AECOM geotechnical team scope of work is to design for the ground improvement using weak drain and then surcharge, and then also geotechnical instrumentation plan, and then monitoring during those surcharge period. And then based on that one, and then we had to do that all foundation design for 9 buildings. Okay, so this is the Canadian Port of Entry. So we have, I already told you that 9 buildings. So 9 buildings, including main building, and then main primary inspection booths. When you're coming into the Canada, and then you have to show that your passport, right? So this is the area, and then this is the important one is the toll booth. So you have to pay the toll to the using the bridges, and also we have large scale image building, which is actually they have some X-ray, and then you can just go through the some of the big truck and the what's inside, and then also the maintenance buildings. And then you can see that, but there is a salt bun. So if there's a lot of snow, and then you have to using salt to make the clean all this road. And then we have a hazmat canopy here. And then what else? I think maintenance, and then client processing building. So 9 buildings actually in the scope of the Canadian POE. Okay, so regional geology. So yeah, so if you are a geotechnical engineer, and then more focused on the soil mechanics, and then maybe you are familiar with about the geologies. The site, regional geology, it is the lay on the physical geographic region of southwestern Ontario, and then eastern Detroit lowland physiographic region. And then it is called the St. Clair clay plain. So which means, if you look at the site over here, and then the project site is located in the clay deposit. Okay, so a little bit more detail. So the overburden is a glacial lacustrine and the glacial till and the till-like soil in Windsor and Detroit metropolitan area. So which means near the river, so there is a lot of the soap deposit, and then in the bottom of the deposit is a till material. They're gonna be combined every type of material together. Just beneath those till, and then there is a limestone bedrock. So we have to look at the geologies, not only the overburden, also you have to know that bedrock geologies as well for the design of any foundation or any design work. Okay, so So basically, based on the some investigation, and then we come up with the soil stratigraphy using all the data. So we analysis, and then as you see, like here, we have about 2 meters of fill, which is the only works. Usually, if you have some P3 project and then owner just preparing the site. So that's why they put it on some fill on the ground. So there is a fill, and then there is old fill and the new fills. And also the below that, there is a desiccated clay. So clay is gonna be a little bit dried and then is over consolidated. So we call it desiccated clay, and which has a little bit higher strength. Then upper clay layer, low clay layer, depends on the index testing, and then also shear strengths and such a things. And then we can, divide into the 2 layers. And then on the bottom, there's a silt layer. This is almost like a tea-like material, which is a more, a granular material on the bottom of the upper bottom. And then we have a bedrock. So, but bedrock is actually keep going. But we just did some kind of modeling only just a few meters. And then one of the challenge in this site is about the artesian water. So if you drill the hole close to the bedrock here, and then the water is actually coming up. So the measured the artesian, what I found in the site is about 6 meters. So if you just drill the hole, and then you can find there are some spring coming up. So 6 meters height. And then also this groundwater contains a lot of hydrogen sulfide gas. So when you expose to the water, exposed to the air, and then it becomes a gas, and then you can smell the rotten eggs. Smells a lot of very strong rotten eggs smell. So it's kind of a challenge to design with the deep foundation. If you just drill through the overburden and then close to this area, and then you have to dealing with all the artesian pressure. Also, you have to dealing with all these toxic gases. So that's why our design is approach it going to do some consolidation, using consolidation theory to doing the pre-loading and then surcharge design and then we can just come up with the shallow foundation for the buildings. Okay, so the properties of the soil, you can see that this is a CPT result, one of the sites in the which is the main building site. And then you can see that silty deposit up to 25 meters. Overburden thickness is average about 25. Some areas 20, some areas 30, but average is about 25 meters. And the blow count on this soft clay area is weight hammer 2-3 blow per 0.3 meters. It's very soft clay. And then so we have to challenge it to about the primary consolidation, also secondary consolidation if you just design for the building. And then I already talked about the artesian, but in addition to the artesian pressure, so we have to dealing with the high groundwater table. So actual, there is 2 different groundwater level. So if you just go to the site and then you have a different layer, have a different groundwater regime. So sometimes ground level in the lower part of the overburden, sometimes there is a shallow water as well. So this is separated, sometimes it's connecting. So you have to know there about the hydrogeologies, how to dealing with all this groundwater. And then we found out there is 2. One is the close to the bedrock, which is very strong artesian water regimes. And also we have very high groundwater, which is about 2 meters below ground surface. And then as I told, artesian groundwater near bedrock and then bedrock is another challenge. Also those hydrogen sulfide gases. So we have to considering all these things. And then we come up with the design with the surcharge, pre-loading, and then wick drain. So I think you are familiar with about the consolidation theory. So if you build some surcharge, then you can see that consolidation is going to be accelerating, and then it's going to be steady after finish the all primary consolidation. So that's why the benefit of the surcharge and preloading is going to be accelerating soil consolidation to meet the some design criteria. If not, and then you have to put the some kind of a building over here, and then it's going to be gradually settled for the long period of time. So you have need more actually considering about the those settlement in your design, and then it's going to be a long-term kind of a crisis. So that's why if you're using the surcharge preloading, and then even using the some weak drain to accelerating the consolidation, then you can save a certain about time. If you have, for example, settlement, the target settlement is about somewhere here, and then if you're using the surcharge and preloading, and then you have a time A, but if you're just not using such a things, and then it will be time 2, and then this difference is going to be reach out to the target settlement. Okay, so some theory. So I'm just going to be touching very quickly. So surcharge theory, the stress is changes from delta sigma G0, which is existing pressure plus surcharge. Then if you just put it in the additional surcharge, then void ratios change from E0 to E1. Because it's going to be compressed, right? And then after the consolidation finishes, and then you can remove all the surcharge, means the original condition is back to the original normal loading condition, but still, E1 to change to E0 not. So still we have this much of a beneficial of the consolidation. And then another, benefit is that the shear strength of the soil increases after the surcharge. So based on this one, you have to think about all these things for your design in the future. Okay, this is the 1D Teriyaki 1D consolidation theory. It's just like, I'm gonna be touching just very simply. So what's the benefit of the to increase the drainage pass? Actually, drainage pass is function of the TV is the constant value, and then if you want to accelerating the consolidation T, then you have to change your drainage pass, the shoulder. So that's why if you're using the some weak drains into the soft clay, and then you can drain all the waters quickly, then actually those consolidation time is going to be reduced. So this is the theory what we're using the weak drain with the surcharge together. So you can see that, if there is no weak drains, and then drainage pass is coming from the bottom of the whatever the groundwater, and then it has to go discharge the water on the surface. So it's pretty long. So this is a drainage pass without weak drain. But if you put it in the weak drain, and then there is a lateral movement between the weak drain, and then the pass is going to be much faster, and then accelerating the groundwater drainage through the PBD. So PBD is a prefabricated vertical drains or sand drains, such a things. So, and then you can just design this distance based on the how much time you need to put those surcharge and the preloading for the in terms of the construction schedule. Okay, a little bit more about the hydraulic conductivity in horizontal, and then how you combine with the vertical drain, and then how that's going to be work. So it's a function of the horizontal consolidation coefficient, and then this is the some kind of a theory. So they're just going to be using the vertical and radial consolidation theory together to come up with the those consolidation acceleration. So okay. And then another theory about the secondary consolidation. So after finish the primary consolidation, then is starting the some creep, consolidation is well with the self weight. So some of the parameter we can get from the laboratory, which is creep consolidation testing, long period of time, and then but this number is gonna be for the just a normal condition. So if you're using the preloading and the surcharge, then we have to think about how this C alpha is going to be changes. So one of the theory just proposed by Dr. Mesri, who's in the Illinois Champaign, and then I think he just proposing this method. And then you can see that if you're using some surcharge and the preloading onto the ground, and then C alpha, which is secondary consolidation coefficient, is actually reduces. So this is the theory. So if you want to know that about the detail, and then you can find it out the paper from here. Okay, and then based on that, we are using the measuring method to determine how we can get the C alpha prime. So you have to using the vertical stress and the final stress, and then you can use this chart to get the some of the idea how much is the ratio between C prime alpha over C alpha. So this is one of the his research, and then it depends on the surcharge loading. So if you have a higher surcharge, and then actually C alpha is reduced much more than less surcharge loading. Okay, and then we just using the another method, because if you do the design, and then if you just rely on one method, and then you just not sure that your calculation or your assumption is going to be correct or not. So always I encourage you can using another method to verifying our calculation for the primary study is going to be correct or not. So we've been using the LAD method to another method to just get the C alpha. And then after that, and then we just compare with the laboratory test result, and then Mesri result, Mesri method, and also RAD method, and then we come up with some ranges between 0.002 to 0.004. This is the this soil behavior. And then as you know that soil behavior differently in different locations. So always you have to have to do those kind of testing, and then you have to find out right method to estimate those coefficient and then parameters. And then the other one is the strength gaining. So we've been using two methods as well. So because one is using the IP, which is the plastic index, which is easily we can get. And then the other one is with the CPT or some other consolidation testing, and then we get using the OCL. So based on these two, and then we compare with the how much strength gaining after the preloading and the surcharge. So we can compare with these two, and then we decide to using the Scampton method, which is the little bit more old method, but when you just compare with the pilot testing. So because it's such a large project, and then they actually building a small bomb or surcharge, and then they actually get the data, and then how it actually behave of the soil. So you can get all this data, and then you can calibrate it based on the actual measurement, and then we decide that Scampton method is more reliable than when you compare with the field data. So we just using two methods, but we found out Scampton method is suitable for winter clay. Okay, this is a weak drain. So when you see that there is a core, which is weak's gonna be here. So this is, and then there is some smear zone, and also there is some surrounding subsoil. So smear zone is going to be changing the hydraulic conductivity. So if it's disturbed, and then conductivity of hydraulic conductivity tend to reduce. So which means it's going to be a disturbed zone is going to be much smaller hydraulic conductivity. So then there is some kind of a relation between radial hydraulic conductivity, also similar zone. So radial one is just outside of the core, not disturbed zone, is much higher hydraulic conductivity. So you have to considering those parameters for your design. Okay, so in the beginning, I just mentioned about the design life is 100. It's not usually 100 years is quite a long time, because if I design at this moment, then after 100 years I'm gonna be die, and then nobody knows it. So it's gonna be all the buildings gonna be standing, okay or not, or it's gonna be sinking down. We don't know, right? So, but a design life is these days is almost 100 years. So. And then this is the PA. So I told you that all the project is based on the project agreement. So when you're starting your work in the consulting engineer, and then somebody already has some experience. So all you have to follow the PA. So this is conformance. And then this is the one of the PA. And then we realized that, so they want to just say that, okay, what is the, you have to follow the, for example, NBCC, National Building Code. And then you have to follow the all the different settlement criteria in NBCC. And then we can actually, asking some of the some relief, because the nature of the soil, and then if you just meet the 25 millimeters of sediment over the 100 years, it's impossible to design. So we just asking to the project owner, say that, oh, we cannot do that, 25 millimeters. So we have to increase our total settlement criteria 50 millimeters. But we want to just keep the differential sediment with the same criteria. So which means, most of the building damage is due to differential sediment, right? So not a total uniform sediment is not going to be just damage on any structure. So we just emphasize such things, and then they accept it by 50 millimeters criteria. And then, so that's why we just design with the 50 millimeters. Otherwise, and then our surcharge period time with the big amount of soil should be sitting maybe 2-3 years, and then we can meet our design, construction schedule, right? So this is the main building, and then we've done some boreholes. So along the all the buildings, so you can see that there is some fill, and then upper clay, and then a lower clay, and then there is some bedrock on the bottom. So it's pretty uniform, stratigraphy. So you can see that most of them is similar clay soil deposits. So there's not much, hiccup or some, unusual behavior of unusual spot of the soil. But you're always thinking about that. You have to enough number of bores to make sure that your design assumption or your design profile, soil profile is going to be confident or not. So if you don't have enough soil and soil data, and then you cannot confident for your design, right? So you can see that how many bores we drilled, 141 bores, and then 49 CPT, and then we installed 58 vibration wire piezometers, and then we have also 38 monitoring well installed it in entire POE area. And then only this main building area, 13 bores, 5 CPT, 8 BWP, and then 4 monitoring wells to be using for the design, only for one building. Also, we're just using some of the surrounding area for the design, for the statistical analysis, for get all those soil parameters. And then also we have some advanced web testing for 1D consolidation testing, 3 triaxial, and then 10 unconfined compression soil testing. Okay, with Victorian design, so you can just choosing what pattern of the Victorian installation. So one of them is a square shape, or another one is triangle shape. So we just selected this triangle, and then we just calibrated our. So this is the some software we call the Set3D. I don't know. So if anybody knows about the Set3D, is about the design program to simulating all the consolidation, and then settlement, calculations stuff. And then there is some input if you're using PBD, and then you have to put some number. So this is, we just put the 3 and 3 as our initial value, okay, for the design. And then we can design of the pattern and then distance of the wick drain, such a things based on our plan for the preloading and then design life. So all things has to be, in the beginning, you have to assume, and then at the end, and then probably you have to back analysis. So that's the industrial practice. So you're just finishing just design as a DD pace, and then if you're not doing the back analysis, and then we have nothing to learn. So this is the important part. So this is all the parameter we're using for our those numerical analysis using Set3D. So this picture, you can see that wick drain. So you can see this small leak is going to be make the pre-treated hole, because we're using the drainage blanket. So if water is coming out from the wick, and then it has to be moving quickly. So drainage blanket, we already put it in the sites. So that's why this machine cannot go through the those granular layer. So that's why we have to make the hole. Then they're gonna be putting this one. This actually installation very quickly. So maybe one hole takes maybe a couple of minutes. So they're just gonna be put a lot of wick drain rolling in the the bathroom tools, bathroom tissue, and then put it on the top, and then just push it into the ground, and then cut down. That's it. So it's pretty. A lot of wick drain we installed it here, but actually one by one, it doesn't take too much. Okay, so C alpha value based on the test result, and then we got this one, and then our theory based on the measuring, and then also a lot, and then we can come up with a similar number, 0.002 to 0.045. So we can select it as one of the number for the secondary consolidation for our settlement analysis. And then even after the removal of the surcharge and preloading, and then usually we have some rebound, because the soil is that elasticity. So after compression, then if you relieve of the stress, and then it's gonna be recovery. So that's the rebounding time. We calculating about 30 to 45 days. So then you have to do working on it, because during the rebound time, if you're adding another one, and then we cannot predict the final settlement correctly. So this is the final design of the surcharge, and then surcharge, and then you can see that's about 56 meters wide on the crescent, and then the width is about the length is about 173 meters. It's a huge one, and then height is about, I think total height about 8 meters. So this is really huge, the surcharge for the one building. So you can see that this is the one of the after construction of the surcharge bomb on the main building. Main building was the critical path for our construction schedule. So we actually initiated the surcharge building in this area at the first time. So you can see any other place doesn't have any surcharge, right? And then you can see some of the monitoring points here. So this is the monitoring point. So we've been using the WP, so which is checking the pore pressure. So the consolidated theory, if you put it in the surcharge and preloading, and the pore pressure increases, and then when this pore pressure dissipated with the water is discharging, and then soil is consolidating, right? So that's why you have to check that out where this pore water pressure is going to be stabilized or not. based on using the BWP, vibrating wire piezometer. And then settlement place, so we have to checking out how much is settled on the ground actually. And then also on the side, because of the, the slope stability, if there is a loading and if there's any failure, and then actually soil is moving here and there. So that's why we have to using inclinometer to check that out, the soil stability. So those are the associated with the main building only. And then after the waiting for 1 year and I think 1 year and 3 months. Yeah, so we've been waiting for those time, and then we say that, oh, I think it's now is stabilizing all the the proper water pressure. So it's time we can remove those surcharge. So this is the indicator of the all the BWP. So you can see that this is the DB level, our level based on the our surcharge, and then this is going to be the measurement on the time. So in the beginning, so based on all the investigation and the laboratory test result, and then our assumption, and then we predicted about 1.4 meters of settlement within the 9 months. So this is our original design. It is detailed design basis. And then we have to compare with our actually field measurement. And then we found out it's actually come up with only 1.2 meters. So where is the 200 millimeters is gone? So that's why we have to studying the back analysis based on the some post construction investigation. Also, we have to revisit our parameter, and then we can just come up with some of the idea. One of the issue was that actually, we just using only 3 layers of clay. One is the desiccated, and then upper, and then lower. But if you make the more discrete layer, I think everybody know that if you make it more layers, and then your prediction is more accurate. So that's why we just look at our data again, and then we can divide it into two, 1 layer into 2. So we can using some of the this is a slightly over consolidated clay, normally consolidated clay, and then another normally consolidated clay. So we just divide into 2 layers. Also, we just change the our ratio of diameter of the smear zone from 3 to 4, and then also smear zone is going to be increased to 3 to 4. And then some of this idea is coming from the CPT result after the preloading. So you saw that the previously the original parameter, and then the new design parameters. So we have the back calculation, and then you can see that OCR changes in the desiccated clay, which used to be 1, and then we have to put the another layer, and then we change the OCR rate, and also we change the CHCV, so which is the coefficient of ratio between horizontal and vertical coefficient of consolidation, changes from 2 to 1, and then also a lower layer increases, reduce 3 to 1, 3 to 2. So we're just trying to matching our prediction with the actual field data. And then this is the after the back analysis, and then you can see that there is a dotted line is the measurement, and then the continuous line, which is dashed line, but this is showing that actual our final element modeling result. So you can see that pretty good matching. And then even this area is we just using the exact location of the we were measuring, and then you can see that the behavior is pretty good agreement. And then we just want to check that out, how much strength gained after the surcharge and preloading. And then you can see that there is a CPT result, and then all the shaded one is coming from before construction, and then all this blue line is after the construction. And then as you see that So we have several locations we did it. So you can see that the strength gaining in some location, but especially this one doesn't seems to be have any strength gaining. So that's why, why we have a same period of time, same height of the surcharge, and then we find out that this location has uniform soil. The why we have a different result. So that's why, okay, then we have to look at the, we just take the subsample from there. So we just take the sample, exact location where did CPT, and then we found it out. So there is, this is top and this is bottom. So if you extrude the soil sample through the Shelby tube, and then we found out there is a silt layer. So because we didn't catch these things during the investigation, we just assumed that this area has all the clay. But there is a little bit of maybe 1 meter thick, or I don't remember exactly, but very thin layer. We have a clay, like a silt. So that's why there is no strength gaining. And then we did this testing on this area. So that's why we don't have a much increase in our strength gaining. So you can see that effect of due to the drainage condition. So because this is a huge land, so and then we can put the drainage is as like a blanket, and then all the PVD. But the water has to be coming up, and then it has to be go somewhere to discharge. But sometimes it's gonna be stuck in one location because of the poor drainages, or the gradation of the those blanket is not correctly done. So that's why the water just accumulating in one location and it does not moving. So that's why there is a back pressures. Also, there is no improvement. So that's why the drainage is going to be important. So that's why we had to make the some kind of remediation method. So which using additional surcharge to meet the our design criteria. So some of the location. So that's why you can look at the in the future, and then there's an additional surcharge we had to add in during the period of the surcharge. And then if you're using the good drainages, you can see that there's a good movement. So if you have a big, large, area of the surcharge, and then close to the edges, is easy to water can get out, but in the middle, usually it's not. So in these cases, we have to using some horizontal drain connecting with the vertical and then hit discharge. But always contractor doesn't want to spend money, right? So so that's why we had some issues. We just proposing this one, but it's okay. So we can figure it out, and then we found out such a thing, and then later on the contractor has to pay more to adding surcharge, right? Okay, so this is the set 3D analysis. You can see that each of this point is the foundation, and then small like this foundation, the other foundation. So this is the how much settlement is going to be done for this. Okay, so now is the more interesting part is about site photos. Okay, so all right, so this is the original sites. So we don't have anything. So you can see that just like some of the only work to put the some granular material as a drainage blanket, and then we didn't have anything over here. And then you can see that this is tower, starting the those tower, and then and then they start building some buildings. Okay, so this is the drainage blanket that they just put it in the main building area. And then after that, they just put the all the those PVD, so big drains. And this is first stage of the construction of the surcharge. Because of the power pressure, it increases. If power pressure is increases, and then shear strength of soil is decreases. It's a soil mechanic, right? So, and then that's why we have to wait a certain period of time to dissipate those power pressure to stabilizing the strength of the ground. So first stage about 4 meters, and then waiting about 3-4 months, and then we just look at the for pressure changes, and then, okay, this is good, and then you can put it another layer. And then this is the final one, and then you can see that there is another patchy. So this is the area we don't have the soil stress gaining, so that's why we're adding another 1 meter on the patch. So there is some remediation works because of the side slope is gonna be because of rainfall, and then it's going to be some of the we just made. Okay, so this is the our analysis with the Z3D, and then this is the actual construction of the footings of the main building. Okay, so this is the recent photo, so you can see that our main building is here, so is connecting with the primary inspection booths, and then return bridge is here, and then maintenance buildings, LSI, so large scale image building, and it has a canopies, and then the service is somewhere here. Yeah. So this is the recent photo, and then stormwater ponds is all designed and then well constructed. Okay, so another photo is about this port of entry. So in the future, if you go to the United States, and then you can coming back in this way. And then you can see that this approach bridges to the bridges. Okay, the conclusion. The first one is, the ground response is vary from your plan. So if you just, your prediction is always correct with the actual behavior, is great, but sometimes not. So that's why if you have a detailed design, there is an uncertainty, so you have to go a little bit conservative design, okay? And then be flexible. So you have to always think about the back analysis after the DD phase, and then after construction, and then you have to verify your design, your assumption is correct or not. So always you can put it in your plan or your budget for this kind of a back analysis, especially for large scale project. And then when you review all data, so you have to review all data. So not only the one location, but also the other location. And then you have to just looking at some kind of conclusion. So you're just looking at only one result and then just make a conclusion. So that's going to be some issues in the future. So you have to combine many other data at the same time. And then considering plan B, so if your design doesn't work, and then you have to think about plan B in advance. So if the soil is not consolidated very much, and then you have to prepare an additional surcharge in advance to tell your clients this is the critical, you have to do this one, such things. And then be positive means, yeah, in the future you're going to working with the clients, and then sometimes you don't want to so my design is correct, and then your direction is not correct, and then you're just asking too much such things, right? So, but you have to be positive, and then you have to make the solution together. So, some of the professors say that who's your team on your consulting business? So actually everybody's a team. Owner is your team, also contract is your team, and the consultant is your team, and the contract is your team. So working as a one is good for, and then is going to be a way of success of your project. So good relationship with your clients, and then also owner is your partner, part of your team. So you don't have to against them. So always be positive, and then also just trying to make the good working environment together. Okay, so thank you. And then this is the our design team, and then you already know that the Dr. Gao here, and then the Ja Hee, and then who's now is in city of Brampton, but why just purple? They are from Western, so. Okay, so any questions?
questions from the audience? Probably only a quick one, because, yes, Leonardo.
I do have one question about the back analysis on part 5. When you notice that the field measurements were not matching the design, out of all parameters, how did you know that it was the OCR and dividing that clay layer into 2 that was the main concern?
Okay, so that one is actually, we just went through the CPT result, and then we found out there is some different, result. So that's why we just decided to put it in the much more layer. But I think the Dr. Always can answer more accurately if I'm.
I can explain a little bit more on that, because when you do your initial design, when you review all your data, so you already start to making assumptions, right? Like you start thinking, okay, how we're gonna model it, how we're gonna design it. You gotta start to separating the solid layers. At that point, in your mind, you should start to thinking, okay, something I make, that's probably too wet, right? Like that's not accurate or like not accurate enough. So that will be your initial thoughts, like at the first stage of design. But at that time, I was thinking, you have to thinking either way, like this assumption gonna make you more conservative side or aggressive side. So usually my style is first step is go on the conservative side. Then you get a room to improve. That's why we have additional data like a CPT and the verification, everything, the additional investigation or whatever the information comes in, I can look, okay, if that is the case, kind of conservative prediction. Aggressive. So that is just kind of design approach, because once you have the kind of projects on your hand, from the step 1, you start to make assumptions, because there's no way you can get absolutely correct or like a certain for the geotechnique, right? Like unless you drill everywhere, like 1 meter apart or half meter apart of wall, like through the entire land, then you can get a better understanding. Because from the beginning, you start to make an assumption. So that's where okay, this set of parameter probably give you the little conservative part, but more practical if you don't have this kind of experience. Do a sensitivity analysis. Selecting all those kind of consolidation parameter, doing a sensitivity analysis, they will give you the response. Which one is more significant? Which one is less significant? Then you get an idea. And this is probably the key parameter I should target it for, right? If you're changing like a tenfold or something for one parameter, then like 7 that doesn't change. That means this is irrelevant, right? So that's just a general.
If you have any other questions, please feel free to come by afterwards, but I think it's time.